On September 17, 2023, Wales changed the default speed limit on restricted roads from 30 to 20 miles per hour. This chart shows provisional casualty data for the first 4 complete quarters following implementation. Police recorded casualties on 20 or 30 miles per hour roads dropped from 2,402 down to 1,725. That exact decline of 28.18% is a mathematically verified fact. But that mathematically verifies absolutely nothing about whether the speed limit policy actually caused the decline. When we evaluate a national intervention, we must distinguish between an accurate description of the data and the actual causal effect of the policy. Confusing the two leads to false confidence. The problem hidden in the official casualty dataset is a structural failure known as a non-injective observation map. In a non-injective map, entirely contradictory real-world outcomes seamlessly produce the exact same piece of observable evidence. We are going to prove this by stepping through a strict causal audit of the frozen aggregate data. By building a constructive mathematical witness, we can demonstrate exactly why any causal conclusions drawn from this specific dataset must be halted. If we bypass this structural check, we risk anchoring national policy decisions on statistical noise rather than measurable impact. Let's start with how the data is measured. The official statistics bin all casualties on 20 and 30 mile per hour roads into a single category. This chart shows the composition of that combined bin. It is a constantly changing mixture of pre-existing 20 mile per hour roads, the specific roads affected by the new policy, retained 30 mile per hour exceptions, and later reversions. Crucially, the frozen evidence does not provide a versioned historical map showing which specific road segments actually changed limits. Without a geographical map linking casualties to those precise segments, the actual treatment effect of the policy is absorbed into the noise of the combined categories. You cannot isolate the true effect of a new intervention when your measurement tool only tracks a fluctuating combined mixture of treated and untreated subjects. We have to separate the descriptive proxy, that 28% drop across all combined roads, from the true causal target, which we call the estimand. This comparison table defines both targets. The registered causal estimand requires measuring casualties strictly on the specific road segments where limits actually changed and comparing them against their specific counterfactual. That counterfactual, the number of casualties that would have occurred on those exact same roads if the policy had never been implemented, is unobserved and completely missing from the data. Without explicitly isolating the causal estimand from the combined proxy, analysts risk mistaking a broad demographic or seasonal shift for a specific policy outcome. You cannot take a flawed descriptive proxy and use it as a substitute for a rigorous causal estimand, simply because the proxy is the only number you have on hand. To test if this proxy can actually identify a policy effect, we build a constructive witness. We construct hypothetical counterexamples to see if the data can distinguish between them. This table locks on the official aggregate data. Before the policy, we observed 2,402 total casualties, which we will split as 2,000 on affected roads and 402 elsewhere.
During the policy period, we observe 1,725 total casualties, splitting as 1,000 on affected roads and 725 elsewhere. We will hold those observed totals perfectly constant. Now we introduce the missing counterfactual variables, the unobserved no policy outcome and the implied causal effect. In World 1, assume the unobserved no policy outcome was 2,000 casualties. Compared to our observed 1,000, that yields a highly successful negative 50% causal effect. In World 2, assume the unobserved no policy outcome was exactly 1,000 casualties. This yields a 0% causal effect. The policy did nothing. In World 3, assume the no policy outcome would have been just 500 casualties. That implies the policy actually caused a 100% increase in casualties on those roads. Look at the observed outcomes. All 3 of these completely contradictory causal realities are perfectly compatible with the exact same observed aggregate drop, down to 1,725. Because the aggregate data comfortably supports a negative effect, a zero effect, and a positive effect, it mathematically differentiates none of them. This chart illustrates the mathematical breakdown. 3 distinct causal starting points map directly into a single observed endpoint of 1,725. This is a non-injective observation map. These percentages are counterexamples proving the failure of the evidence. They are not measured estimates, and they are not confidence intervals. Because the inputs collapse into one indistinguishable number, we cannot trace the path backwards from the observed data to uncover the true cause. The frozen evidence cannot identify a point value for the policy effect, and it cannot even identify the basic sign of the effect, whether casualties went up or down due to the change. Therefore, any point estimation based on this specific dataset is analytically unjustified. This audit does not conclude that the 20-mile-per-hour limit failed, succeeded, or had zero real-world effect. It establishes that the widely reported 28% attribution is unsupported by the frozen official evidence. This diagram maps the discipline of identification before estimation. When an observation map fails, this identification gate glows red, blocking calculation of an effect estimate. When evidence cannot distinguish contradictory outcomes, researchers halt attribution. The output is a constructive non-identification result. Stopping at non-identification prevents the illusion of measurement, protecting policy evaluation from resting on false confidence. This image represents the data structure required to actually measure the policy's impact. We need localized collision data linked directly to a precise geographic map. Evaluators must first freeze a versioned historical map documenting the exact segments that changed to 20 miles per hour, the exceptions that stayed at 30, and any segments that later reverted. Then, they must link individual collision records and local traffic volume specifically to those identified segments. Waiting for more quarters of aggregate data will not resolve the issue. More time will only feed more noise into the same broken observation map. Reproducing a descriptive statistic is only the first step. Without a valid causal map linking the treatment to the outcome, those aggregate numbers remain descriptive facts, but causal fictions.